This is video 6 from the GCSE Physics video series. This one's all about molecules and matter. Now there's a few ways we can describe matter, material properties that we can use. Well, here's one of them, density. Density is a way of describing how much mass there is in a particular volume of matter. So we've got an equation here to calculate the density. Mass divided by volume. And that is equal to the density. Now a key thing here, and I've made it subtle on this particular presentation, the key thing here is that P is not rho. Rho is not P. Actually, the first letter I've written here is rho. Do not confuse it with the Roman letter P, the Greek letter rho. There are different letters. The Greek letter rho kind of like the equivalent to the Roman letter R. Nothing to do with P at all. I know they look similar, but there are differences. Notice that the ascending part of the letter is written with a slight curve to it. There are different ways of writing it. You can write it so that the curve goes like this, or you can write it so the curve goes like this. Some people start from the middle and write down. Some people go from the middle and curve it this way. They're all acceptable rhos because they all have a rounded part at the top left corner. Whereas when we write Roman letters, we almost always start from the top left and draw it straight down, back up, and then round for the curly part. That is a very different letter. It's got a pointy bit on the top left. Now, the reason why this is so important is because later on we're going to have equations that have both a rho and a p in them. And if you've learnt density, or that's a p, then you're going to have problems, because it's not. It's the Greek letter rho. Sometimes I've seen notes, textbooks, where they use a d for density. But this is not good. We use a rho, so let's stick with that convention. Right, so if we want to measure the density of a substance, we need to be able to measure the mass of that substance and the volume of that substance, and therein is a problem. You can measure the volume of a gas or the volume of a liquid quite easily. With something called a gas syringe, you can measure the volume of a gas, or with a measuring cylinder, you can measure the volume of a liquid. So measuring the volume of fluids, such as gases or liquids, no problem. Measuring the volume of a solid is much more difficult. You can determine the volume of a solid by making measurements of the length, width, and height, length, breadth, and depth of the object. If it's a regular shaped object, you can make measurements and then use geometry to calculate what the volume is. For example, a cube. You measure the height of it. If it definitely is a cube, then you only have to measure the height and then cube that, times it by itself twice to get the volume of the cube. You don't want to trust that it's a cube just because something looks like a cube, so you would measure the 3 different dimensions, and you'd measure them multiple times and take a mean, and then you would multiply those 3 dimensions, those 3 different lengths together in order to get the volume calculated. So you can calculate a volume. Measuring the mass is easy. You just get a balance and stick the mass that you want to measure onto it, the object, the body you want to measure onto that balance. If it's a fluid, then you're going to have to measure the mass of the container of the fluid before you add the fluid, and then after you add the fluid, and then subtract the mass of the container to calculate what the mass of the fluid is. And I'm saying fluid because it could be a liquid and you're using a measuring cylinder, or it could be a gas and you're using a gas syringe. What if I've got an object which is not a nice regular shape? So I can't just measure some lengths and calculate a volume. Well, in that case, we use something down here. It's called a Eureka can or a displacement can. It's got those 2 names. The Eureka can is named after 𝗟𝗶𝘀𝘀𝘀𝘀 expression of joy when he found what he was looking for. So I'm not going to go into that story. So, or the legend, the apocryphal story. But there we go. So this is sometimes called a eureka can, sometimes called a displacement can. It is just a can, usually made of copper, with a nozzle. What you can do is you can fill it until it is overflowing with water, then stick a measuring cylinder underneath the nozzle and then add the mass, the object, that you are trying to measure the volume of. It will displace the water that you filled this can up with. The water is pretty much uncompressible. So because, or incompressible, let's get our English right. So because the liquid, the water, is incompressible, the object itself isn't going to squash the liquid down. It's going to push it out of the way, which means that the volume of water displaced, which pours into the measuring cylinder, will be equal to the volume of the object which has displaced it. Which is fine, you can use that to measure the volume of the object. Of course, if the object floats, that's a problem, and you might have to get something like a very, very, very small volume, a very thin pin, just to push it just under the water, in order to be able to make a measurement of the volume of that object. So that's why I've drawn this very thin line coming off it there. It might just be a pin pushing it down, but there we go. If it's an irregular shaped object, a non-porous irregular shaped object, then you can measure its volume indirectly by displacing water. So then we can calculate the density. We can't directly measure the density. We can measure the mass, and we can determine the volume either by measurement, if it's a fluid, or by measurement of a displaced fluid, if it's an irregular shaped object, or by calculation if it is a geometrically regular shaped object. But anyway, we can determine the volume, and then we can use that to calculate the density. We do have to watch out for units. So the density of water is one of those numbers that chemists like to memorize. It's 1 gram per cubic centimetre, which is 1 gram per milliliter. 1 milliliter is equal to 1 cubic centimetre. It is important to know that these two volumes are equivalent. So you can measure the density of water, and you'll find that that is the case. If I have a litre of water, then that is going to have a mass of 1 kilogram, so 1,000 grams. Water has a density of 1 gram per milliliter, or 1 gram per cubic centimetre. But do be careful, because in physics we often choose to use kilograms per cubic metre. We use what is called the kms system of units rather than the cg system of units. Sorry, the MKS. I've got those letters in the wrong order. I thought I said it wrong. The Oh, go back a slide. What are you doing? We tend to use the MKS rather than the CGS system of units. These are both metric systems of units. CGS stands for centimeters, grams, seconds. MKS stands for meters, kilograms, seconds. There we are, I got it right in the end. So this is what physicists would prefer to use. It is actually what the international community has agreed is the appropriate system of units to use. It is the SI system of units, SI units, System International. So kilograms is the SI unit of mass, meters is the SI unit of length, which makes cubic meters the derived SI unit of volume, and hence water has a density of 1,000 kilograms per cubic meter. Now, I'm not going to go into unit conversions in this video, but you do need to be able to convert area units and volume units, including prefixes, as part of your GCSE, which is not super duper straightforward. I've just dropped my pen. Let's go pick that up. I'm not going to edit that out. So this is 100 cubic centimeters is not equivalent to 1 cubic meter. That is just incorrect. It's just not true. Because, well, especially not the way I've written it. Should we try that again? Mistakes all over the place. 100 cubic centimeters is not equivalent to 1 cubic meter. It's just not true. 100 centimeters is 1 meter, but 1 cubic meter is 1 meter times 1 meter times 1 meter. So it's 100 centimeters times 100 centimeters times 100 centimeters. So 100 times 100 times 100 is 1 million. 1 million cubic centimeters is 1 cubic meter. I'm not going to go into lots of detail about that, and I'm not going to do lots of practice converting areas and volumes. You will need to be able to do that as part of your GCSE, though. But do just be a little bit careful when you're doing these conversions. It's handy to remember that 1,000 kilograms per cubic meter is the density of water, which is exactly the same, is equivalent to 1 gram per cubic centimeter, which is 1 gram per milliliter. That can be handy to remember. Minor things, so if you've got a density greater than water, you're going to sink in water. If you've got density less than water, you're going to float in water. That should have been covered in year 3 of primary school. I don't think primary school science is necessarily always well delivered. Sometimes it is, sometimes it's not. Well, it's like anything. Sometimes it's well delivered, sometimes it's not. So, year 3 was a long time ago. You might have forgotten it as well. But there we go. Density is what affects whether something floats or sinks. Well, it's not quite true, but that's what I'll say for now. Right, mass. How do we measure the density then? I've got some instructions here. Measure mass using a balance. Determine the volume. We've talked about that. And then use equation. That's it. A couple of things left to say. When we're measuring volume using a measuring cylinder, we need to make sure that we are viewing the surface of the liquid using at perpendicular to the scale to minimize, to reduce, maybe even eliminate the parallax error that would happen if you were viewing this bottom of the liquid from lots and lots of different angles. You would get different measurements. So to reduce or even eliminate that effect, we view the surface of the liquid at perpendicular to the scale. We make sure that the measuring cylinder is on a flat surface. That means we don't lift it up to measure it. We don't sort of lift up our measuring cylinder and look at it. We get down low to bring our eye level to the surface of the liquid. I'm avoiding the word meniscus. I'm now going to bring in the word meniscus. If we're measuring water, you'll find the meniscus curves in this way. So there's a lowest point to the meniscus here. So if we're measuring the volume of water, we are going to measure from the bottom of the meniscus. There are liquids where the meniscus goes the other way, in which case you measure from the top of the meniscus. But usually we're interested in something like water or some solution where water is the solvent, and you end up with the meniscus curving down. We measure from the bottom of the meniscus, eye level. And that's all I'll say about that. So that was lesson number 31. Here's lesson number 32. And I don't want to spend a long time on this because states of matter is really quite basic as a topic. These sorts of NAF diagrams you can find all over the internet. These are stolen from Wikipedia, used under Creative Commons license, where particles arrange themselves in a nice regular pattern for a solid, less regular for a liquid, and all over the place for a gas. Of course, these are not great diagrams. For one thing, what are the containers made out of? Because if the containers aren't made out of particles, then what are they made out of? If they are made out of particles of the same sort of size as the particles that the container contains, then why can't I see them? Secondly, these are very small containers. Thirdly, you can have solids where the particles within them aren't arranged in a nice regular pattern. amorphous solids, we call them, and glass is a good example of an amorphous solid. So that's not always true, that they arrange themselves in a nice pattern. We can also see often they're shown where the little blobs representing particles, which could be atoms, but they could be molecules, so I'm going to use the general term particles. Usually people draw them in a solid where they're touching. Well, that's not quite true either. They vibrate and oscillate around fixed positions. That is true. Whether those fixed positions are a regular lattice or an irregular arrangement, they still have the particles oscillating, vibrating around fixed positions. And they can't do that if they're touching each other. So they don't touch each other. Density of a liquid is similar to the density of a solid, but here it's drawn that the liquid is lower density than the solid because the spaces between those particles are bigger. And that's not always true either. It depends. So with water, the liquid density is greater than the solid density. But with iron, the liquid density is lower than the solid density. So, solid iron is going to sink, whereas solid water is going to float. Solid iron sinks in liquid iron, solid water floats in liquid water. But in general, the densities aren't that different. They're very similar. So your liquid density is very similar to your solid density. This doesn't really show that. Then we've got a gas, and the distance between these is nowhere near sufficient. If this were truly a to scale representation of a gas, then the chances are this container would contain nothing. If you get lucky, you might get one particle, which in this case the particles appear to be these two blobs stuck together. So maybe these are representing atoms, not particles on this diagram. And two of them stuck together as a molecule. And in this case, we probably call the molecule, the two of these blobs stuck together, the particle. I will clarify particles, molecules, and atoms in a minute. Anyway, so if you get lucky, you might get one of them in this volume. And if you get supremely lucky, you might get two. But gas density is significantly lower, 1,000 times lower than liquid density. So you're not going to see anywhere near as many. If you had 1,000 particles in your liquid in a certain volume, then you expect to get one particle of gas in your volume. Sort of, on average, kind of, roughly. Let's clear up this particles versus molecules versus atoms thing then, because a lot of textbooks talk about molecules all the way through this topic. I've got a bit of a problem with that. I've got a bit of a problem with that because you could have something like neon gas, where neon gas consists of atoms that are moving around and bouncing around. The atoms don't combine to form a neon molecule. Now, you could argue that a neon molecule has a single atom in it, and that is all. But it seems like a stretch to me to call a single atom a molecule. I think a chemist would be happy with that, probably correct, but I don't know, it just rubs me up the wrong way. So, I don't know. We also get situations like where we have sand, and sand can flow similar to a liquid. It's not a liquid. It contains small grains that are solid. So where does that fit in with this? If it can flow, flour, sugar, that sort of thing. So this is a really rough, almost very babyish, juvenile picture of what's going on. Anyway, particle is a general word that we can use to describe the smallest unit of a particular type of matter. So if we have something like neon or even iron, you might say that the smallest unit is an atom, although in iron they bond metallically, so you'd say the smallest unit perhaps is an iron ion. But those smallest units, if I took my helium gas and I took a container of it and I cut it in half and cut it in half and cut it in half again and again and again and again and again, I would still have helium or neon or argon or any noble gas until I get to a single atom. Now, if I try and cut that in half, then I've stopped having that particular element. I've cut the atom in half. So for something which is an atomic substance, we could say that the atom is the particle. But something like water, that doesn't quite work. So with water, I could take a container of water and I can cut it in half and still have water, and then cut that in half and half and half and half again until I've got a single molecule of water, H2O. Now, if I were to cut that in half, I've no longer got water. Depending on how I cut it, I might just cut one of the hydrogens off, and then I've got hydrogen gas and oxygen monohydrate or monohydride. I don't know, monohydrogen. I don't know what a chemist would call that. I'm really, really not a chemist. Or even hydrogen monoxide. Hydrogen monoxide, maybe they would call that. Hydrogen monoxide. And hydrogen. Boom. Neither of which is water. We've got rid of the water by cutting the water molecule down further. So the particle of water is a molecule of H2O. The particle of helium gas is an atom of helium. And if we talk about something like cathode ray, which we'll talk about in physics much later on, maybe even in A-level, don't doubt we'll get onto it in GCSE level, or if we talk about alpha radiation, for example, or even beta radiation. Gamma, pick one, doesn't matter. Let's go with beta radiation. The smallest unit of beta radiation, the particle of beta radiation, is the electron, and you can't cut that down any smaller. If we take alpha radiation, the smallest unit of alpha radiation is a helium nucleus. You cut that down smaller, you've not got alpha radiation anymore. So there are examples like that where we're not talking about atoms and we're not talking about molecules. We're talking about electrons, we're talking about nuclei, we're talking about other sorts of particles. So particle is a general term for the smallest unit of matter, of a particular type of matter. And I would prefer to talk about particles all the way through this rather than molecules. But if your notes say molecules, if your textbook says molecules, hold it lightly, as I say. It's absolutely fine. Right, so we've got these. Now let's look at changing state from one state to another. Solid, liquid, gas, and of course we also have plasma as a fourth state of matter. A plasma is even more energetic than a gas. But let's have a look at the process. So if we have a solid and we turn it into a liquid, we're melting that solid. Liquefaction, melting. If we have a liquid, we're turning it into a gas. We are vaporizing that liquid to make it into a gas. Now, you'll find textbooks that talk about evaporation. That's fine. Evaporation is a process that turns a liquid into a gas. It's not wrong. But I'm just going to label it vaporization here rather than evaporation. Because at the moment, I don't want to get into fine detail about the difference between evaporation and boiling. That will come later. A gas transforming into a liquid, condensation. A liquid transforming into a solid, freezing. If you are educated in some parts of the world, you will learn that liquid into a solid, that process is called solidification. Liquid into a solid into a liquid is called liquefaction or liquidation. No, liquefaction, I think. Can't remember that one. But liquid into a solid, they'll call solidification. And they will reserve the words freezing and melting for when we're using water. It makes them feel uncomfortable talking about taking molten iron and freezing it at temperatures over 100 degrees Celsius, over 200, over 500, over 1,000 degrees Celsius, over 1,500 degrees Celsius. Okay, so iron freezes at a very high temperature. So freezing iron could be 1,000 degrees Celsius, and it would be frozen iron, which confuses some people, so they would prefer to use words like solidification instead of freezing. But here in the UK, we use freezing, melting, vaporization, condensation, or condensing, and vaporizing. We've changed the form of the verb here. Bit naff, but there we go. Solid to a gas, everyone remembers, sublimation. And I have heard the reverse process referred to as sublimation as well, and the reverse process referred to as reverse sublimation, usually by chemists, but there is a better name for it. It's deposition. And there are different ways of doing deposition, which is turning a gas into a solid. You can have, for example, chemical vapor deposition or physical vapor deposition. It does depend on what you are, the substance, the matter that you're changing from gas to a solid. In general, this is the process. We increase temperature, so we put energy in. We are heating to go from solid to liquid, from liquid to gas. That energy is going into the thermal energy store of the substance, so the liquid and the gas have more energy in their thermal energy store than the solid does. And cooling, so removing energy from the thermal energy store, is going in the other direction. If we continue to put energy into a gas, we can make it ionize. So gas into a plasma is ionization. Plasma into a gas is called either deionization. Don't know if I like that word. Deionization. Yeah, that would work. Or sometimes it's called... No, we'll stick with that. Deionization. So ionization from a gas into a plasma. But don't get that confused with things like deionized water. That just means it's water where they've removed any other ions from it. So it's just pure water. So you've got plasma all the way over here somewhere on this particular chart. So it says here, when the substance changes state, there's no measurable change in mass. And that is true. There's no measurable change in mass. When you do A-level, we'll talk about the change in mass that can be measured, E equals mc squared and such. But at the moment, we're only at GCSE level. Let's keep it simple. There is no mass change that I could measure on any apparatus in my lab. So for all intents and purposes, for the calculations we are doing, a kilogram of solid, when turned into a gas, is a kilogram of gas. So then we've got this chart, this table down here, talk about state and some properties of that state. You can kind of read that yourself. I'm not going to go into that too much. Over here, kinetic theory of matter. This is a technical term, which means we are considering the matter to be particles which can move around. Maybe they vibrate, maybe they move around each other in the case of liquids where the particles don't occupy fixed positions and vibrate around those fixed positions. The particles are free to wander around, or a gas. So movement and arrangement of particles, we call that the kinetic theory of matter. Particles, here we go. I've already talked about the energy that they have. We increase the energy of the particles by changing state. Solid, liquid, and gas. Earth, air, and... well, earth, water, and air, I guess, as they used to say in the ancient Greek times. We've moved on from that. Right, let's move on to lesson number 33, I think it is. Yes, lesson number 33. So lesson 33, changes of state. And you can see I've put that diagram, there it is, get my finger right. I've got that diagram there that we had before, showing the different state changes we're interested in. But we also have a graph here. And this graph shows the amount of energy I have put into a certain mass of substance. In this case, it's water. And on the y-axis, the temperature that that substance, in this case it's water, has reached. And let's say I've got a kilogram of water to keep it simple. It starts as a kilogram of solid water, which we like to call ice. And we put energy in. Now let's imagine that I'm using a heater of constant power. If I'm using a heater of constant power, then the x-axis is, well, it is energy, but it could be time, because time multiplied by power is energy. So energy is directly proportional to time. So you could think about this as me having a constant power heater, and this is time on the x-axis, and the graph would be exactly the same shape. So I'm going to put energy in, and as I put energy into my solid water, otherwise known as ice, the temperature increases, and then it stops increasing. Now this is the case for pure water. If you add salt, then you can reduce the temperature when this happens. I'm not using horrible words like plateau. I'm not a geographer looking at mountain formations. Stop using the word plateau, please. All we're talking about here is the gradient of this graph becomes 0. Don't say it goes flat, it's constant, things like that. I mean, you could say it was constant if it was time on the x-axis. That would make sense to say the temperature is constant. But this is energy on the x-axis. So we could just say that the rate of change of temperature with respect to energy is 0. It's 0 gradient. Now, actually, this graph is going to show a slight curve here, but this is an idealized, simplified case. Let's have a quick drink. Apologize. So we increase temperature, and then water, when it reaches 0 degrees Celsius, pure water, the temperature stops increasing. But we're still putting energy in. And after some time, after some amount of energy we've put in, we now have liquid water. So during this process, we have a mixture of solid and liquid water, of ice and liquid water. Now, the ice cannot be above 0 degrees Celsius, and the liquid water cannot be below 0 degrees Celsius at standard pressure, standard atmospheric pressure at sea level for pure water. You cannot get liquid water under those conditions below 0 degrees Celsius, or solid water in those conditions above 0 degrees Celsius. So while you've got a mixture of the two, the water stops the ice getting colder. That wouldn't happen because I'm putting energy in, so the ice stops the water, the liquid water, getting hotter. So we continue to put energy in, and it doesn't go into the energy store associated with the kinetic energy of the particles that make up that substance. It's going into another store, but it's all part of the thermal energy store. We're putting energy into the thermal energy store, but the particles aren't moving faster, although on average I suppose they might be because they're free to move more. I'll have to think about that. The amount of energy that we put in during this process of melting, we call the latent heat. This particular process, melting, we call the latent heat of melting, or more generally, the latent heat of fusion. Now, if I were taking liquid and putting it into a solid, using terms like latent heat of fusion would make more sense because the molecules, the particles that make up the water are free to move around each other in a liquid, and then I'm sort of locking them in place for a solid. And that's not fusion in a nuclear sense, it's not nuclear fusion, but we are fusing those molecules together in some sense so that they can't move past each other and change their relative positions. So that's the term that we use, and we could actually use the term latent heat of fusion for both, for both directions through this process, for melting and for freezing. It's just the way it is. You find some literature that says latent heat of freezing, latent heat of melting, but the GCSE we do prefers to call it latent heat of fusion, and it's fine. Then we continue to put energy in. The temperature continues to increase for the water up to 100 degrees Celsius. And then the liquid water can't get to a higher temperature under these conditions. Pure water, standard atmospheric pressure at sea level. So I continue to put energy in, but the temperature can't go up. What happens is the liquid water cannot be at a higher temperature than 100 degrees Celsius, but the liquid water is transforming into gaseous water, steam. Yes, steam is what we're going to call gaseous water. If you can see the particles of it, like what comes out of a kettle, that's after the steam has dropped temperature a little bit, and we now have what's called a vapor, which will condense back into a liquid in little droplets, and that's why we see it as a cloud. So you can't actually see steam, but you can see water vapor. So clouds aren't made out of steam, for example, because you can see them. So this latent heat of vaporization is the energy that's transferred during the change in process from a liquid to a gas. Vaporization, no problem. And in reverse. Sometimes it's called latent heat of condensation, but it's the same thing, latent heat of vaporization. And then we increase in temperature. Now, there's a subtle point here. You'll notice that the gradient of the line at the beginning and at the end is pretty much the same, but the gradient in the middle is lower. And that's important. If you remember when we measured specific heat capacity, when was that? That was a much further back in time. Let's see if I can find where it was. Specific heat capacity we measured... Oh, blimey. Was it in the thermal energy section? I'm scrolling back. Yes, there it was. Lesson 13, 2.4. In lesson 13, we measured specific heat capacity. We had energy transferred versus temperature, and we used the gradient to determine the specific heat capacity. Remember that the gradient was directly proportional to specific heat capacity. We just divided the gradient by mass to get the specific heat capacity. So the gradient of energy transferred versus temperature is proportional to specific heat capacity. Well, what we're doing is we're looking at the process here, and we've got temperature versus energy transfer. It's the other way around. So the inverse of that gradient, the reciprocal of that gradient, is proportional to the specific heat capacity. So this gradient is actually half as much as this gradient, which means the specific heat capacity of liquid water is roughly double the specific heat capacity of solid water, ice, and gaseous water, steam. It's just the way it is. Now, there are reasons for that. It's to do with hydrogen bonding, and we can talk about that at some other time, maybe, but it's not something that's required for your GCSE in physics, but you might be interested in it for chemistry. Why is that the case? For now, we'll just accept that it is. And there we go. That's an important graph. Now we can change the boiling point. That's the temperature here, which is labelled 100 degrees Celsius. And we can change the freezing point, or melting point as it's usually called, which is down here, 0 degrees Celsius for water. We can change that by adding impurities to the water, such as salt. Very popular to do that in the winter. Add salt to the roads so that the ice will freeze at a lower temperature, which means that we are at negative 10 degrees Celsius outside, less likely to get black ice on the road that will make a car skid. Evaporation can happen at any temperature. This is true. Any temperature where you've got liquid water, even if you've got liquid water at 0 degrees Celsius, from the surface of that water, the most energetic particles of water, that is molecules of H2O, the most energetic ones can leave the surface of that water. You can get that process happening for solid water, for ice, but we wouldn't call it evaporation, we'd call it sublimation. And you can get sublimation from ice as well. As a matter of fact, this is what happens on comets. In comets, which are in the vacuum of space, there isn't a liquid state for water. You need air to be pushing down to ensure we have a liquid state for water. The lower air pressure is, the lower the temperature of that boiling point for water. And when air pressure is 0, because you're in space, then the boiling point of water and the melting point of water are the same points. So there's no liquid state. You just go from solid straight to gas. But solid into gas can happen at any temperature as well, although it's lower likelihood to happen, which means we get very little solid water sublimating and turning into a gas. It can happen. But liquid water evaporating into a gas, that happens quite a lot. If I have a puddle out on a brisk autumn day or something, maybe it's 10 degrees Celsius outside and I have a puddle, I might notice that at the start of the day the puddle is one size, and by the end of the day the puddle is much smaller. It might even have gone altogether. Where's the puddle going? Well, it's not absorbing into the concrete, although perhaps some of that is happening. It's evaporating, and the puddle's not boiling. Okay, the water is only going to be the same sort of temperature as the surroundings. It's going to be in thermal equilibrium. But the most energetic molecules of water are the ones that leave. As those molecules leave, the most energetic ones, the ones with enough energy to break out of the liquid water, that happens at the surface, because any molecules deeper are going to be smashed back in by the rest of the liquid molecules. As that happens, the average energy of the molecules that's remaining has dropped because the most energetic molecules are leaving. So that actually has a cooling effect on the liquid, which is how sweat works. When we sweat, the sweat evaporates, cooling our skin and the liquid that remains. It's not a whole drop of sweat evaporates in one go. If we've got a little droplet of sweat on our skin, then that droplet of sweat will reduce in temperature as the surface liquid molecules, water molecules of the sweat, evaporate away. So evaporation actually cools the remaining liquid. Some people would think evaporation, well, okay, we're turning liquid into a gas, so that must increase the energy. Well, it doesn't. What we're doing is we're just removing the most energetic molecules from the surface of the liquid, which means the average energy of the molecules left is lower. So it has the effect of cooling the substance, which of course also reduces the rate of evaporation, which is why the likelihood of a puddle completely evaporating is well, it takes longer and longer to evaporate over time. Boiling happens at the boiling point. Now, what happens there is we got the process changing from a liquid to a gas for the most energetic molecules, but particles, keep it general, but the most energetic particles that have an energy high enough to leave the liquid can now be found anywhere in the substance. Rather than just at the surface, because anything deeper, there's enough around that's going to be bashing it back in. That's not what happens anymore. So now you get liquid turn into a gas throughout the liquid volume. So you see bubbles. And that's what the clue is that you've got boiling, is lots of bubbles emerging from your liquid. And at that process, any more energy you put in is just going to go to turning liquid into a gas anywhere in that substance. We're not just removing the most energetic from the surface. They're all getting up towards that highest energy that a liquid particle, the particles in a liquid can be while still being liquid. We're getting up to that point. So there we are. Boiling and condensation happen at the boiling point. I've already talked about that. Melting and freezing happen at the melting point. Energy transferred. I've talked about all this. You can read that yourself, but I've talked about all this already. So let's move on to lesson 34. Lesson 34 is about internal energy. Now, internal energy is another way of saying thermal energy, but it's a little bit more subtle than that, because sometimes when we talk about thermal energy, we really are only interested in part of the internal energy of the substance. But in general, if we talk about transferring energy into the thermal energy store, we're talking about transferring it into the internal energy store. Internal energy of the substance consists of two, I'm going to call them components. The particles can move around, which means the particles have a kinetic energy. But also the particles are not necessarily free to leave the substance. In a liquid or in a solid, the particles have a lot of energy, yes, but they are attracted. There are intermolecular forces holding those particles in that substance. And as the particles move farther apart, there's more and more energy stored in those potential energy stores. In the same way as if I lift an object higher, away from the Earth's centre, by the position of this object in the Earth's gravitational field, I change its potential energy, its gravitational potential energy. All we're talking about here is an electrostatic potential energy. Now, you remember looking at electric potentials in the electricity topics. This is the same sort of thing. So we've got these atoms. Let's take a simple example here of, let's say that this is positively charged, the one on the left, and the one on the right is negatively charged. So it's a simple ionic bond between these two atoms, a little bit more complicated with covalent, but the same principles apply. So we've got these two atoms, these two ions of opposite charges, and electrons come off the one on the left and gone on to the one on the right. Now in chemistry, you'll talk about there being a bond between them. It's a bit naff, it's not very good science, but that's what chemists talk about. And a chemist will tell you that you can break that bond if you put enough energy in. Again, it's a bit naff, but that's what they say. Now, these molecules will all have these forces between each other as well, these intermolecular forces as well as intramolecular forces. As these molecules, or even the atoms within, the ions within the molecules, move farther apart, we store more energy. In the same way is in the electrostatic potential energy store now, instead of the gravitational potential energy store. It doesn't matter, we're storing energy. Now this is oscillating backwards and forwards. What we've got is a transfer of energy from one store to another. When it's moving, there's energy stored in the kinetic energy stores of the bodies, of the ions. When the ions stop moving, which happens at the extremes of their motion, then the kinetic energy stores are depleted. But the energy is now stored in the electrostatic potential energy stores. And that's what we see, is energy transferred from the kinetic energy store to the electrostatic potential, back to kinetic, electrostatic, kinetic, electrostatic, kinetic, electrostatic, kinetic, electrostatic potential energy stores. That's what's happening. Now, the total amount of energy in this particular molecule might not be changing. And then you've got the whole substance, so you've got molecules interacting with each other as well and oscillating around as well. But it's the same principle. The total amount of energy is not changing, and we can call that the internal energy of the substance. When I put energy into this substance, I can do one of two things. I can either put energy into the kinetic energy stores of the particles, and I can do that by colliding them with things, which is what happens in thermal conduction, for example. Or I could put energy into the potential energy stores. And this is what can happen if the particles are getting further and further apart, and I carry on putting energy in. I carry on pushing them farther and farther apart. So I can put energy into either of these two stores, and probably both of these stores. And together they make, as a plus in the middle, together they make up the internal energy. Now the kinetic energy store is related to how fast the particles are moving. And so that manifests as a macroscopic temperature. The faster the particles move, on average, the higher the temperature of a substance. So the mean kinetic energy per particle, that's related to something I can measure. I can't measure the kinetic energy of a particle in a substance. It's too small, they're all moving too fast, and I don't have anywhere near enough good equipment anywhere in the world to measure that sort of kinetic energy. But I can measure the temperature of the substance, and people cleverer than me worked out that the temperature is the physical way of measuring, or the physical manifestation, the macroscopic physical manifestation of an increase in mean kinetic energy per particle, an increase in temperature, and vice versa. The particles are oscillating around a certain point in a solid, but if I'm able to get those particles to move farther apart, for example, in a liquid, if I consider just two particles, I ignore all the other particles of liquid, I just look at two of them. In a solid, they're oscillating around a fixed position. But in a liquid, they can oscillate and get further and further apart from each other. They can move their position. So that means that they are increasing the distance between them, and just like we talked about with the gravitational potential energy example, that causes an increase in the electrostatic potential energy that one has stored due to the other one. So the other one particle has stored due to the other one. So the change in state from solid to liquid causes an increase in the potential energy on average of the particles, and therefore the total potential energy of all the particles in the substance. And the same going from a liquid to a gas. So as I'm putting energy into my ice, I start by energy going into the kinetic energy stores of the particles that make up the ice. The particles move faster and faster. But then remember, the temperature stopped increasing. That's what we saw on this graph. This is from the previous lesson. So then as the temperature is no longer increasing, but I'm still putting energy in, that energy is going into the potential energy stores. And then when the temperature increases again, instead I'm putting energy into the kinetic energy store. And then when the temperature stops increasing, because, looking at the previous lesson again, I'm now up here, changing state from liquid to a gas, The temperature's not changing, so I'm putting energy into the potential energy stores. And then if I continued to heat my gas, I'd be putting energy into the the kinetic energy stores of the gas. And if I continue to increase the temperature, eventually I'm going to be ionizing that gas, turning it into a plasma, and I would be putting energy into electrostatic potential energy stores again. So you can see you're putting energy into one, then the other, then one, then the other. There's a simplification because in most substances during the state changes you are actually putting energy into both, but for simplicity's sake this is what we say. So the physical macroscopic manifestation of changing potential energy is changing state. And the physical macroscopic, that means on a scale I can see, macro means big, macroscopic, on a scale I can see, the physical macroscopic manifestation of changing the kinetic energy stores of particles is the change in temperature. And the total, we add up the kinetic energy of every particle in our system, and we add up the potential energy of every particle in our system, we add all those energies together, that total amount we call the internal energy of the substance. Another name for thermal energy, but now we have gone deeper. And sometimes thermal energy, we're only interested in the kinetic energy part. Whew. That was complicated. So particles, all particles experience forces of attraction. I'm not talking about bonds. I don't like talking about solids become liquids because bonds get broken. It's not quite good enough. What we can say is the particles have enough energy that the work that would be done by those particles as they move apart against that force of attraction is greater than the work that would need to be done for those particles to... I've got myself tripped up here. If they don't have a high enough temperature, or if the particles don't have enough energy, then they don't have enough energy for them to escape each other. As the particles move apart, the force of attraction between them causes work to be done, and if they don't have enough energy, then not enough work can be done before the particles fall back towards each other. And so we call that, we imagine there's a bond there. But if we give the particles enough energy, then as that force of attraction is acting, the further apart they get, the weaker the force gets. And so eventually they've got so much energy that that force isn't strong enough to hold them together. It's not true that the force weakens, and this is something chemists will say. At higher temperature, those bonds weaken, the forces of attraction weaken. It's not quite true. It is true that as the particles get farther apart, the force weakens, and it is true that they can get farther apart because the particles now have more energy, and therefore more work can be done before they stop moving, before the kinetic energy store is depleted. That is true, but in the same way as sending a rocket into space, you wouldn't say it's broken the bonds of Earth's gravity, although I think they did used to say that in the 50s and 60s. Wouldn't really say broken the bonds with the Earth in order to escape and send it to Mars, a rocket, for example. We wouldn't really say that, and it's the same thing with changing state. That's my rant about this. Chemists talk about breaking bonds. You ask a chemist what is a bond and then watch them scratch their head. They'll talk about electrons transferring, which has nothing to do with what's going on here with our intermolecular forces, our interparticle forces. But there we are. Average kinetic energy stored per particle is high enough that the force of attraction between them is insufficient to bring the particles back together, which is why particles appear to move randomly in a fluid. I tried to write it in the smallest space as possible. It all comes down to work done equals force times displacement. And if you've got enough energy, then you can displace far enough that the force is so weak that you can continue to displace with the energy you've got left and never come back together. So you're breaking your bond is what a chemist would say it. So fluid pressure caused by collisions. Right, now this is an important point. Look at this box containing particles bouncing around. I'm not interested in the particles colliding with each other. I'm really not. I don't care about that. If I'm talking about measuring pressure, I'm interested in the collisions between the particles and the walls of the container. Every time a particle collides with the walls of the container and changes direction, it's because the walls of the container have pushed that particle back. And Newton's third law, if the walls of the container have pushed the particle back to make it change direction, then the particles have pushed the walls forward. Okay, so the walls are being pushed out by the particles as the walls push the particles back in. Again, Newton's third law. And it's that that produces this effect of pressure. You can't measure pressure without a surface for the particles to hit, for you to feel what that force is on that certain area of surface. We don't talk about successful collisions either. When we talk about how particles colliding with the walls of the container causes a pressure, students will talk about successful collisions because that's what they've learned from chemistry and it's stuck in their head and it sounds good. Well, no, there's no such thing as an unsuccessful collision in physics. It's something collides with something else. It collides. We're not interested in whether or not there's sufficient energy and probability works well so that electrons can happen to transfer over, and then we've made a molecule where before there wasn't one, and blah, blah, blah. We're not interested in chemistry and the probabilities. If two things collide, they collide. So successful collision doesn't make any sense in physics. Don't use that terminology. There's a little thing here about gas potential energy stores being high because the particles are far away, and then they're comparing particles and the forces between them to masses on springs, just to try to get you clear in your head the idea of kinetic energy, potential energy, kinetic energy, potential energy. Imagine a spring that could be both compressed and extended. Has a natural length, and if you squash it in, it pushes outwards, and if you stretch it out, it pulls inwards. You put a mass on each side of that, and then push them together and let go, they'll oscillate like this. Of course, we've got difficulty showing this on Earth because gravity pulls the whole thing down and it hits the floor, and then friction stops everything moving. But, okay, we're looking at individual particles, and that's what's going to happen. They're going to shake like this, backwards and forwards, energy being transferred between the masses and the springs, the masses kinetic energy and the springs potential energy and the masses. That's our model. It's not actually a spring, though. It is electrostatic forces between our particles, whether they're intermolecular forces or intramolecular forces. The forces between molecules or the forces within molecules. It doesn't matter. It's all electrostatics. Right. I'm going to move on to lesson 35 now. So in lesson 35, we come back to specific latent heat. Specific latent heat, which we talked about a couple of lessons ago. Now on the top right, I've got a different equation. And perhaps I shouldn't have put that equation there, but I have. This is the equation for specific heat capacity, which is a different quantity altogether. Yes, it has the word specific in it, but it's not the same thing. Not at all. So just because it's got the word specific, keep reading. Specific heat capacity. Now the word specific means divided by something. In most cases, we mean divided by mass. So specific heat capacity, specific latent heat, specific charge. You'll do that in year 12. Specific means divided by mass, usually, for us. So the heat capacity would be the amount of energy that is transferred to bring about a certain change in temperature. That's the heat capacity. Divide that by mass, you get the specific heat capacity. But we're not looking at that. I just threw that up there to remind you of a term that is similar sounding but means something very different. This is what we're looking at, this equation at the bottom. We use an L for specific latent heat. Now, unfortunately, sometimes the exam board forgets the importance of the word specific and they just talk about latent heat. Latent heat, technically, is the E, the energy transferred to potential energy stores of the particles in the substance. That is what we mean by latent heat. Divided by mass, we now have specific latent heat. So we can measure specific latent heat of fusion, for example. Here's an experiment where we've got an electric heater. We can measure the potential difference across the electric heater, the current through the electric heater, use that to calculate the power of the electric heater using that equation we met in a previous video. Then, using that power and a stopwatch, we can measure the time it takes to change the state of solid to a liquid. In this case, it's ice into liquid water. And multiplying that heater power by time gives us the energy we've put into the ice. Now, if the ice was at 0 degrees Celsius to start with, and the water that we collect at the bottom is at 0 degrees Celsius, then energy has not gone into the kinetic energy stores of the particles that make up that substance. So where's the energy gone? It's gone into the potential energy stores. It's changed the state from solid water, ice at 0 degrees Celsius, to liquid water at 0 degrees Celsius. And so if we capture that liquid water and measure the mass of water using a balance, not a scale, we never call them scales, measure the balance, measure the mass using a balance, then we can determine the energy that we've transferred, just said how to do that, divided by the mass of water collected. That tells us the specific latent heat of fusion. Latent heat is the heat transferred, the energy transferred in changing state. Specific latent heat is the energy transferred in changing state per kilogram of mass. So specific latent heat of fusion, energy transferred per unit of mass that changes from a liquid to a solid or vice versa. We could do the same thing for vaporization by boiling water, measuring the mass of liquid water, putting energy in at a certain rate with a stopwatch, and then measuring the mass afterwards. The difference is going to be the mass of water that turned into steam and left the liquid water. And we can do the same thing. Right, let's move on, because we've been talking for an hour now. Move on to lesson number 36. So there's I think it's 2 lessons left. Might be 3 lessons left. 2 lessons left on this video. Gas pressure and temperature. So this equation at the bottom here, you are given. The equation at the top we cover in more detail in a later video, but I'm just going to define pressure here because it's hard to talk about pressure and temperature, the relationship between them, if we don't know what pressure is. So even though we define pressure properly later, let's start with this pressure definition. Pressure is force divided by area. Now, a very minor thing, remember my little comment I made in a previous video about bold letters. Bold letters indicate vectors. So force is a vector, it has a direction. But so is an area a vector. It has a direction. If you don't believe the area has a direction, imagine it's raining and I hold out a sheet of paper and I hold it out horizontal. It's going to get very, very wet. But if I hold the sheet of paper vertical and it's raining straight down, it's the same area, but it gets less wet because more water misses it. So the direction of the area matters. Area has a direction. So what we're doing here is we are calculating the pressure using the component of force, and we'll talk about vectors and components in a later video, hold it lightly or watch the whole series twice. So the component of force perpendicular to the area vector, parallel to the area vector, which means perpendicular to the surface. Now, I'm not going to go into more detail about that because area vectors I talk about extensively in A level, and you don't really need to know it for GCSE. It's just for completeness I wanted to make sure that the vector nature of area and force were included. Don't worry about it. Pressure is force divided by area is all you need to remember. And the force should be perpendicular to the surface of that area. So, more force on the same area, more pressure. Same force on a smaller area, more pressure. So that's why with a drawing pin, there's a very thin, sharp end, and there's a big fat end. You push the fat end with a certain amount of force, the same force is going to be exerted on the other side of the pin. Because there's a big fat end, you feel less pressure on your thumb than the wall feels from the sharp end of the pin. So the pin goes into the wall. So that's what pressure is. Force divided by area. Another thing is, we're going to talk about the way that gases behave. We need to use a new unit of temperature. I'm sorry, it's just the way it is. When Celsius's temperature scale was chosen as the standard, where 0 degrees Celsius was the freezing point of pure water at atmospheric pressure, 100 degrees Celsius was the boiling point of pure water at atmospheric pressure. When that was decided, it seemed very sensible, and we used thermometers calibrated to those numbers. However, we have already found out, let's go back a few lessons, that in terms of internal energy, the more kinetic energy a substance has, the higher the temperature is. What's the minimum amount of kinetic energy that the particles in a substance can have? Well, I suppose that would be 0 joules. The particles stop. And when the particles stop, we can't reduce the kinetic energy of those particles anymore. We just can't. And if we're talking about a gas, not a solid or a liquid, but a gas, then there's nothing in the potential energy stores because the particles are so far apart, they're not interacting with each other. So there are no electrostatic forces of attraction between them. So for a gas, the potential, what we call an ideal gas, don't worry about that, the potential energy stores is 0 anyway. So for a gas, if we get the particles to stop moving, we remove all the energy from them, there's no more energy we can take out. We can't reduce the amount of internal energy of that substance anymore. It's at 0. So in that case, we need to say that the temperature is 0. And the reason for that is, with a gas, as I double the internal energy, I double the kinetic energy, I want that to double the temperature. That would be really helpful. That would be a lovely unit of temperature to use. It's called the absolute temperature scale, and we measure it using a unit called Kelvin, not the degrees Kelvin, the Kelvin. So we have measured the temperature where all the particles stop moving. So a temperature that you cannot get lower than. You can't reduce the temperature. We can only remove energy from a substance by having the particles bang into us so we can take that energy away. If the particles are stopped moving, I can't take any more energy away. And the temperature when that happens is the same for all substances. It is negative 273.15 degrees Celsius. At negative 273 degrees Celsius, all movement stops. And so we now have a new unit of temperature, the Kelvin, and we say 0 Kelvin. But we keep the interval of 1 degree Celsius, the difference in temperature between 29 and 30 degrees Celsius. We keep that interval the same as the interval on the Kelvin scale, on the absolute scale. So the difference between 300 and 301 Kelvin is the same as the difference between, 27 and 28 degrees Celsius. It's the same interval of 1 degree C is the interval of 1 Kelvin. So we've basically just shifted the origin of our graph for the kinetic energy versus temperature. We've shifted it so that when the kinetic energy is 0, the temperature is 0. Okay. For two variables to be directly proportional, a graph of them has to produce a straight line and pass through the origin. We've now got a temperature of 0 when the kinetic energy is 0. And the temperature will double if the kinetic energy doubles. So we've now got direct proportionality between temperature and the kinetic energy of the particles in our system. So that's if we use the Kelvin scale, the absolute scale. We shift the origin. So negative 273 degrees Celsius, add 273, we get it into Kelvin. 0 degrees Celsius, add 273, we get it in Kelvin. 100 degrees Celsius, add 273, we get it in Kelvin. Or doing it the other way around, 0 Kelvin, subtract 273, we get it in degrees Celsius. 273 Kelvin, subtract 273, we get it in degrees Celsius. 373 Kelvin, subtract 273, we get it in degrees Celsius. So you can see that all we're doing is either adding or subtracting 273. And you've got to remember that number. You've got to. You need to know that. And how to do these conversions. Now, why are we doing that? Because if the particles have stopped moving, so the temperature is 0, then they are not colliding. Let's go back a page or two. They're not colliding with the walls of the container anymore. Remember lesson 34. They're not colliding with the walls of the container if they have stopped. Let's go back to today's lesson, this lesson. So when the temperature is 0, the pressure must be 0 because the particles stop moving. And if we double the temperature, we double the pressure. The pressure and temperature are directly proportional. Particles are moving faster, they collide more often, and because they're moving faster, more force is needed to change their momentum, make them turn around and go back the way they came. So both of those things increase the force on average, which therefore increases the pressure. Double the temperature doubles the pressure. So this equation, where this is just some number, some constant, this equation is one that you are given, but you need to be able to use it. Most situations, you'll be given a pressure and a temperature either before or after some change. Then you'll be given either the pressure or the temperature after some change, and you'll be asked what's the other variable. So you just have to calculate the constant from one situation and use it in the next situation. So fluid pressure, so gas, liquid, that sort of thing. Fluid pressure is caused by collisions between fluid particles and walls of the container. That's crucial. Now, we could have the walls being, for example, the edge of a piece of soot. So there's a little bit of soot. This was first noticed. This is what we call I think it was Robert Brown. I'm sure it was Robert. Someone will correct me if I'm wrong, or I can look it up later. But Brownian motion is the name of the motion of a small piece of soot or pollen that you might see, a little speck that you might see, moving in a random way, wiggling around in a random walk. And it looks completely random. It was determined, it was observed that this is happening because the little piece of soot is being struck, is being bombarded, collided on all sides by something that must be really small because we can't see it. And therefore, if it's really small, must be moving really fast to be able to cause the changes in motion that we observe from that little piece of soot. So this was the first conclusive piece of evidence that air contained matter. Air was actually stuff, it was matter. Tiny, tiny little particles of matter moving really, really fast. And they must be tiny because we can't even see them under the best microscope. We can see the soot under the best optical microscope, but we can't see the air particles. So they must be small, but they also must be moving very fast because their collisions are able to make the soot particles change direction. In fact, the speed on average of the particles in air is around between 400 and 450-ish meters per second. It's very, very fast. So here we go. If I've got a fixed volume of gas, so I hold a volume constant, a fixed number of particles in that gas, then doubling the temperature doubles the pressure. They're directly proportional. It just says increasing here, but it is also true that it's doubled. And this is the explanation of why. You can read that yourself. I've kind of talked about that already. So that equation on the bottom left only applies for constant volume, for fixed volume of gas. It doesn't apply for other situations where the volume can change. Which leads us nicely on to lesson 37. In lesson 37, we're looking at the relationship between volume and pressure. And we're going to look at this for when we have constant temperature. So constant temperature, there's a special name for when we investigate the effect of volume on pressure for constant temperature. We call that Boyle's law. Boyle's law says that volume and pressure are inversely proportional, which we can write as an equation like this. So let's look at this picture on the left. Imagine these are particles here that can move around, and I'm pushing them. Right now, when there's none of these blue masses on the plunger, it's only the air outside pushing that plunger down. So it's at atmospheric pressure. The more mass I pile on this plunger, the more force there is pushing down, and therefore the more pressure down. And this plunger will sit at a certain level for a certain for a situation where the pressure outside balances the pressure inside. When the two pressures balance, the plunger's being pushed up as hard as it's being pushed down, because pressure is force divided by area, and therefore the plunger will reach an equilibrium. So what do we notice? As I push the plunger harder, the volume of the gas becomes smaller. Of course, the pressure goes up, because the pressure inside must equal the pressure outside, so the pressure goes up as the volume goes down, and you get this inverse proportionality graph. Not a straight line, it's a curve. That's important. Inverse proportionality is a curve that doesn't touch the y-axis and doesn't touch the x-axis. If you have a smaller volume, the particles have less distance to travel before they collide with the walls of the container. Therefore, the average force is higher. Imagine that it hits the container every second. The average force is what it is. And now it hits it 10 times a second. The average force is higher because over a second, we're pushing it 10 times rather than just one time. So the average force is higher. Smaller volume also decreases the surface area, which also, if you decrease the surface area, increases the pressure, because pressure is force divided by area. So decreasing the surface area increases the pressure. So you've got those two effects, the smaller surface area and the increase in number of collisions per second with the walls of the container, which increases the pressure inside the gas. That's kinetic theory. We're looking at what the particles are actually doing. Now, if I rapidly compress the gas, because I'm pushing, I'm applying a force, I'm going to be doing work on that gas, which means that I'm going to be putting energy into the temperature, into the thermal energy store, into the internal energy of that gas. And remember, if it's a gas, there is no potential energy for the gas, no electrostatic potential energy, so it's going to go into the thermal energy store. The temperature of the gas will increase. This is why a spaceship entering the Earth's atmosphere gets hot. It's because it compresses the air in front of the spaceship, rapidly compresses that air, and it's that rapid compression that increases the temperature. Nothing to do with friction, very little to do with friction. So the rapid decompression drops temperature. That's why when you spray a deodorant can, you'll notice the can gets colder. It's because the gas is escaping, so the pressure inside it is reducing. So rapid decompression reduces temperature. Rapid compression increases temperature. So if we want to do an experiment to test this equation, we need to do it slowly enough that the change in temperature reaches an equilibrium with the surroundings. If the temperature increases a little bit, then it'll radiate more energy through thermal radiation than it absorbs, and so eventually it'll reach back to the same temperature as the surroundings. So as long as you make slow changes to the gas, then you will have the this equation valid. So that's what it says at the top here. You've got to slowly compress or slowly decompress the gas to have this equation correct. If you want to look at the physics of what happens when you do it quickly, well, it's a bit more complicated. We need to use the two equations combined with some other stuff, and then you end up with this rather confusing four-dimensional graph here. I'm not going to go into detail about it. You can mute this and just watch that spinning around if you want to try to unpick what's going on here. Effectively, you've got the red axis, which is pressure, the green axis, which is volume, the blue axis, which is temperature, and then the volume of the gas, I'm varying that. No, not volume. The number of particles in the gas, I'm just varying that over time, oscillating and varying that over time, so that you can see that this shape is changing over time due to that. You've got the curve that you'd expect to get if you look at the relationship between the green and the red, which is the pressure and the volume, which is this. You get that curve, which is exactly what we expect. You get a straight line if you look at the relationship between temperature and pressure. So temperature and pressure is the blue and the red one. So vertical there, red there. If you look at a graph with those, you get this straight line. There it is. That's the straight line we're interested in, which is direct proportionality between temperature and pressure, which is what we looked at in the previous lesson. So this four-dimensional graph contains the full behaviour of gases. But it's not part of your GCSE, so don't panic, don't worry about that. I just put that in there because I like using my GCSE stuff when I teach A-levels sometimes. It makes the A-level students feel really good when you remind them of stuff they did in GCSE that they've probably forgotten. And then you push it further, because that's what A-level's all about. Right, I hope you found that useful. Don't forget, every week during term time, I offer live interactive tuition, which is nothing like these videos, because it's interactive. You sit there, you write on a whiteboard, which I can see and you can see, but no one else can see. All the other students have their own little whiteboards that I can see. So I'll ask a bunch of questions and you can give answers and I can give you feedback and I can mark it in real time and I can give you comments and then you can ask me questions and I can answer them. And there's a chat that goes on at the same time. It's a lot of fun. Students get a lot out of it. So those sessions happen every week. They are dirt cheap. Just go to physicswithkeith.com to find all those details. I'm offering them for GCSE Physics and GCSE Astronomy, starting from September. Never done it before. We'll see if we carry on with it. See how popular it is. But also for for A-level physics as well. But if you're watching this video, it's probably not for you. Right, take care of yourselves, and I'll see you in the next video, which is about radioactivity.